In this video, we will learn the difference between an ideal gas and a real gas. This is for our learning objective for explaining the differences between ideal gases and real gases, because real gases are not ideal. When we talked about the kinetic molecular theory of gases, we talked about how an ideal gas has no attractions between gas particles. In contrast, a real gas does have attractive forces between gas particles. We haven't learned about intermolecular forces yet, but all particles have some degree of attraction between them. So there are attractive forces between real gas particles. Also, we have in an ideal gas a negligible particle volume, but since all gas molecules, all atoms are matter, they do actually occupy volume. And so at a certain point, you have to actually consider what volume is occupied by the gas particles. We find that gases behave much like ideal gases at STP, which is standard temperature and pressure. This is a graph showing the molar volume, that's the volume of 1 mole of gas, and everything. So if we plugged 1 mole of gas in at STP, it would occupy 22.4 liters. And then you can see here that the other gases are also really close to 22.4. Some of them are exactly 22.4. But there are some deviations. For instance, chlorine gas isn't 22.4, it's only 22.06. And carbon dioxide is 22.31. And so both of these are lower than what you would expect based on the ideal gas law, but still very close to ideal behavior at STP. Real gases do not behave like, do not behave like real gases at high pressures and low temperatures. Let's talk about why that is. First, we have to think about the particle volume. And so at low pressures, we know that the particles themselves are not taking up that much space compared to the whole volume of the container. So at low pressures, the amount of volume occupied by those gas particles is very small. And so we can pretty much just ignore it. And the ideal gas law does ignore it. But as we go ahead and squeeze this down and compress it as much as possible, we do have to consider that amount taken up by the atoms. So if we took our container, and we can't actually push all of the atoms together, but let's say that the ideal gas law says that we should be here. So this is the ideal gas law. That's the ideal gas volume. And we are ignoring the particle volume. But we have real gases, and real gases do occupy volume. And so maybe all the atoms here add on additional space. And so this is the real, I'm going to say that's the particle volume. And so the volume of the real gas is a bit more than the ideal gas law volume. So the real gas volume is everything. Ideal gas law just ignores the volume occupied by the gases. And so as we get down to higher and higher pressures, there's more and more of the space is occupied by the particle volume to the point where we can't just ignore it anymore. So here is that graph showing the ideal gas in red and the real gas argon in green. You can see at low pressures, these two graphs are right on top of one another. You can't even tell the lines apart. So at low pressures, they are identical. So low pressure gas behaves as ideal gas. And then as you get up into higher and higher pressures, the molar volume is more than what's predicted by the ideal gas law. And so we can see here that volume is more. Volume is more for the real gas. And that's due to the volume of the atoms. In 1873, a scientist named Johann van der Waals modified the ideal gas law in order to solve and do a correction. And so we know that PV is equal to nRT. And so what he did is he solved for volume. So he got nRT over P. And then he had a correction factor. You can see this is added to make the real gas a little bit more than ideal. So we have our volume is going to be a little bit more than ideal. And so this N here is the moles. And B is a constant that you're going to look up on a table. And so that B here does depend on the identity of the gas. This is the first time since we started talking about gases that we're going to have to be specific about which gas we are looking at, because those different gases are going to have different volumes, different sizes, and different intermolecular forces between those particles. So in a previous chemistry class, you might have learned about things like hydrogen bonding, dispersion forces, dipole-dipole forces, and real gases do have those attractive forces between gas particles. And so at high temperatures, the gases are moving so fast that they really don't have time to interact. They're just going right past one another. And so the intermolecular forces are fairly weak because the gas particles are just so energetic that they are not hanging out by one another. But at low temperatures, then they are hanging out more, and so they collide with lower kinetic energy. And so as they collide, they are attracted to one another more strongly because now they actually have time to interact. The amount of attraction is great enough that it can actually make them stay closer to one another. And so those collisions are not actually, the collisions with the sidewall are not really as hard because they are being attracted to gas particles within the rest of the gas. So here's some pictures to show what I was talking about. In ideal gas, there's no attractive forces between the particles, but in a real gas, there is attractive forces in between the particles. So in an ideal gas, if this particle here is going to be slamming up against the sidewall, there's nothing holding it back. But in a real gas, as it goes slams into the sidewall, now we have all these attractive forces kind of pulling back on it, saying, no, don't hit the wall, don't hit the wall. And so it's like, all right, well, I'm still going to hit the wall, I just won't hit it as hard. And since it's not going to hit the sidewall as hard, then that means our pressure is going to be lower than ideal. And so here we have a subtraction correction. And so much like before, we take our ideal gas law, PV is equal to nRT. That's ideal. We solve for P. And then we do a correction to account for what we really observed. And so this correction factor here is going to, so I'm going to write real gas pressure lower. So here we have our correction factor does take into account the amount of particles in the container, the volume, and the letter A here is another constant that you will look up on a table. So now we have to now that we know our pressure of a real gas and we know our volume of a real gas, we're going to use those two equations on the previous slide and set them both equal to nRT. And so that means that we are rearranging those previous equations so that we are setting them equal to nRT. You can see here that we have nRT, so that means we're going to have to add this term to both sides and then multiply by V to bring it over. But that V has the previous correction to it. So this is known as a van der Waals equation, and this will be provided on a reference sheet for your exams, but you just have to be able to use it and identify where things go. So this is the correction factor for intermolecular forces, and this is a correction for particle volume. We can see in this graph when we have deviations from that ideal behavior. So this is known as the compressibility factor Z. And what Z is going to do is it's going to take our PV equals nRT for our real gas and compare it to PV equals nRT for an ideal gas. If they are identical, then we end with a compressibility factor of 1, which is the ideal gas here. And so ideal gases have a compressibility factor of 1. But you can see that there are some deviations from ideal. Like there's a dip here for xenon gas at low pressures. These dips show us when we have really strong intermolecular forces because those gas particles are going to be more attracted to one another, and so our gas is going to be lower pressure than what we expect it to be. And then at higher pressures, you can see that all of these lines are above the ideal gas. That means that those particle volumes are really taking an effect on our gas, and so that's a compressibility factor greater than 1. All right, let's do a practice problem with this van der Waals equation. It says, assuming ideal gas behavior, a bicycle tire with a volume of 1.25 liters is inflated to 80 psi on a hot day, which is 35.2 degrees Celsius. How many moles of gas are inside the tire? So since it says assuming ideal gas, that means that we're just going to be using PV is equal to nRT. That's going to make it a lot easier to solve for n here. And so my n is going to be equal to PV over RT. My P is in PSI, but like these constants are in atmospheres, and I'm given the conversion factor to atmospheres. I know the R value for atmospheres, and so I'm just going to put a period there to make sure that it has at least 2 sig figs. And then I'm going to convert that into atmospheres. I need to cancel out my PSI, so that's going to go on the denominator. I'm making sure to cancel out my PSI. My volume is 1.25 liters. And then my R is 0.082058 liter atmospheres per mole Kelvin. And then I need to convert my temperature into Kelvin. And so to do that, I'm going to add 273.15. and that's going to add up to 308.15 Kelvin. Pretty sure I did that right, but I'm going to get my calculator. I didn't add the 0.2, but get mine. Glad I got my calculator out. Okay, now that I have my calculator out, I can type this all into the calculator. That's 80. And then we're going to do the divided by 14.7 times 1.25. And then that's going to be 0.082058 times 308.35. And so that means my N value is going to be 0.2688 moles. Okay, I'm going to go ahead and store this value in my calculator. I'm going to store it as C so that we don't confuse it as one of these other letters. So I'm going to go Shift Store, and then I'm going to click C. So I'm going to make a note to myself that I stored that in my calculator as C. This number, since my pressure only had 2 sig figs, only the first 2 digits are going to be significant. I gotta remember to put a period on that. Alright, now for the next part of this. It says, if that many moles of N2 is pumped inside a 1.25 liter bike tire at 35.2 degrees Celsius, what would be the real pressure inside the tire? And so that means I'm going to be using this van der Waals equation up here in the corner. And I'm going to be solving for P. The first step to solving for P is to get rid of this V over NB on both sides. So when I can divide both sides by V minus NB, that's going to cancel out that term. And then I'm going to subtract this other term from both sides. And that will give me P is equal to nRT over V minus NB minus A, and then I have to open up parentheses, N over V squared. Now that I have my equation, I can plug in values. I'm going to try to do that underneath here. And then I'm going to just leave my N as N because I got that in my calculator. So I'm going to leave that as N, but then I'll use my calculator value. My R is 0.08205.8 liter atmospheres per mole Kelvin. And my T is 308.35. And then that's going to be over my volume, which is 1.25 liters, minus my N. And then this is nitrogen gas, so I have to look up my nitrogen gas constant. My B is going to be 0.0391, and then the units on that are liters per mole. And then I have to subtract out my A, which is 1.39. And then I have my N value again. I know I left off the units of A. I'm running low on space. And my tablet's not responding too well. Okay. So now I gotta type that all into my calculator. So we have set up a fraction, and I stored that mole value as C times 0.082058 times 308.35 divided by 1.25 minus my moles times my V constant, which is 0.391. And then I have to subtract 1.39, open parentheses, my mole value divided by 1.25, close parentheses, and then I gotta square everything inside the parentheses. And so this gives me a pressure of this many atmospheres. So when this is all done, this gives me a pressure in atmospheres. But I'm being asked for a pressure in PSI. So I'm going to erase this so that I can now convert my pressure into PSI. So I got my pressure, and now I have to cancel out the atmospheres. Hello? Okay, my tablet froze up there for a minute. Okay, we got our pressure in atmospheres. We need to convert it into PSI. And so we're going to be multiplying by 14.7. That's a 7. PSI. And we'll cancel out our atmospheres unit. And so we're going to take our number from before and multiply by 14.7. When I did that and I figured out that it was telling me 80 something PSI, I knew that had to be wrong. I re-looked at my calculator entry here and I had forgotten to type in this 0. And so I found the missing 0 from my B factor, plugged that in, and now I know that my pressure was 5.424 atmospheres. Once that is converted into PSI, that is 14 times 14.7, and that gives us 79.73 atmospheres. And so this is, even when rounded to two significant figures based on the original pressure, it still is 80 atmospheres. But we got 79.73, which was slightly less than our real pressure. So the real pressure should be a little bit lower than the pressure here because of those intermolecular forces between the particles. So our real pressure should be lower, which is how I knew that I must have messed up a little bit. Okay, here's a practice problem for you. Go ahead and pause the video and try to work out the pressure inside of a compressed gas cylinder. Unpause the video when you're ready to check your work. Okay, so a size 200 high pressure gas cylinder has an interior volume of 43.2 liters. At room temperature, which is 27 degrees Celsius, what would be the pressure inside the tank for 263 moles of helium? Let's find out. So we have our equation, which is our P plus Okay, I rewrote the equation up here, and we're going to solve for P again. I'm glad we are not solving for V or N because that's a bit more complicated algebra. So that's going to cancel that out, and then we're going to subtract that A term from both sides and end up with pressure is equal N RT over V minus NB. And then we are subtracting that term from both sides so that it moves over here. And over V squared. And so my pressure is going to be equal to 263 moles. My R is 0.082058 liter atmospheres per mole Kelvin. My temperature is 27 plus 273.15. And so it's 300.15 Kelvin. And then I got to divide that by V, which is 43.2 liters. And then minus my N. My N is 263 moles. And my B is given up here. That is 0.02370. That's liters per mole. And then we got to subtract out this A times N over V term. That's 0.0342 liter squared atmosphere squared per mole squared. And then over N, which is 263. Squared. This whole thing's going to be squared. And my volume was 43.2. That's a bit messy. Okay. So here we go. 263 times 0.082058 times 300.15 divided by 43.2 minus 263 times my B, 0.02370. And then I have to subtract out my A, which is 0.0342 times open parentheses 263 divided by 43.2 close parentheses, and then I got to square that term. And so that's 173 atmospheres. So my pressure is equal to 173.9 0.59 atmospheres. I'm going to round that to 3 significant figures, and so that's going to be reported as 174 atmospheres. One last conceptual problem for you. What conditions is a gas most closely related to an ideal gas? High or low pressure? High or low temperature? Go ahead and pause the video and write down your answer, and then unpause the video when you're ready to double check. So a real gas is most similar to an ideal gas at low pressure and high temperature, because we want our gas particles moving really fast so that they don't interact with one another. And we want low pressure so that they're really not interacting with each other that often.